All right, we've hit noon, so good afternoon, everyone, and welcome to our first MEGUG Lunch and Learn of 2026. I'm Matt Doobie, the Vice Chair of MEGUG, and I'm joined by Becky Schaffner, our new chair, who's taken over for me after 3 years. Today, we're going to be talking about SQL and ArcGIS and how they relate to one another, a talk meant to bridge the training spaces that different professionals have. In the intro slides here, I've placed a QR code in the bottom right if you'd like to become a member of MEGUG and you currently are not. Please feel free to snap that at any time. It will be in the same place until we introduce the speaker. We'd like to announce that our next upcoming Lunch and Learn is tentatively scheduled for February 11th at noon. Dr. Alex Burnham of the Department of Biology at the University of Vermont will be joining us to talk about the space-time cube data format and a library for Python and R that he and his NSF grant team have been working on recently. Spacetime, because it's part of both of Python and R, is completely free, so it's a good tool to be seeing in the community. If you have ideas for future Lunch and Learn topics or would like to do a Lunch and Learn talk yourself, please shoot us an email at the email in the slides here. As we do at all of our Lunch and Learn meetings, we'll take this time to acknowledge our sponsoring organizations that make our programming possible: CAI Technologies, Esri, Main Technical Source, and Viewshed at the gold level, Maine Department of Agriculture, Conservation and Forestry, the Maine Department of Transportation. Why does this keep moving forward? The Maine Office of GIS, the Maine Public Utilities Commission, the Raymond H. Fogler Library at the University of Maine, and the Wheatland Geospatial Lab at the University of Maine as silver sponsors. And the Maine Geo Library, CGIS Solutions, Dirigo Spatial Systems, the Greater Portland Council of Governments, GEI Consultants, St. George Consulting Group, Stantec, Stone Environmental, Wright Pierce, and the Kennebunkport, and Wells Water District as our bronze sponsors. Thank you to everyone. As a point of business, we have a series of bylaw amendments being voted on by the membership currently. If you have not voted, please check your email and vote on these changes. Please cast your votes if you are a member. That closes at midnight on January 18th, which is this Sunday. And now for today's talk. Today's talk will be given by me, not in my MEGUG capacity, but in my professional capacity. I'm an associate professor of data science at the University of Maine in Augusta, and I also work with several graduate programs at the University of Maine, and have worked as part of the Geo Libraries Board as well as the Maine Geospatial Institute. So, Becky, if you have anything you want to add about questions and answers during the talk, I'll let you do that now, and then we'll move forward.
Sure. For questions about Matt's talk, please put them in the Q&A, and we'll get to them after the presentation. Just use the chat for any issues you're having with the Zoom presentation itself. Thanks.
All right. So let's go ahead and begin today's festivities. Today we're going to talk about something that is quite important in the world of decision making. And too often people who come to something like GIS without a computing background lack knowledge of this type of area, not necessarily because of their own doing. Similarly, for those who are more on the computing side of things and the business side of things, you likely learned about SQL as part of your undergraduate education, but maybe have had to brute force your way through GIS. If either of those describes you, this is the place for you to be. We're going to talk about how the two of these things philosophically intersect, namely, how do I accomplish something from one of them in terms of the other? I'm not going to live demo this, but I'm going to show the types of screens in ArcGIS where these types of functions occur. My goal here is to get people to think from a tabular point of view, because independent of whether or not you fully know or leverage SQL right now, thinking in terms of that will be great help to you in solving data query tasks, particularly when they become much more complex. So over the next 45 minutes or so, we'll follow this general course of action. I'm going to introduce myself so that you trust that I know what I'm talking about. Then we'll talk about what a GIS is from the perspective of a data scientist. Because that's going to leverage related tables by default, we'll talk about how relational databases are organized and what we need databases to be able to do in general. We'll then talk about what SQL is and talk about its structure and basic order of execution. Finally, we'll talk about how the features of SQL show up in mechanical steps you take in a GIS. Though I will demonstrate this through ArcGIS, these types of tools are common to virtually all GIS in some way, shape, or form. No matter how you would do them in ArcGIS, and you may have learned how to crosswalk them to another application, these same concepts will exist. All right, so I already introduced myself as my professional title in that I have an affiliation with MEGUG, but I'll add that my formal training is in mathematics and in spatial temporal data science. If you were to look at my CV, you'd see lots of things that are either applications of GIS to social problems, or you'll most notably for this conversation today see things that are about formalizing relations between objects, similarities between those relations, or formalizing scenes or data mining approaches to find perhaps shorthand ways that might be easier to declare a relation between objects from. In other words, I'm someone who theoretically builds the blood and guts of GIS query systems, mostly because I have the mathematical background to be able to do that sort of thing across lots of different types of data. If you're keeping track, that probably qualifies me to teach lots of different types of things in my day job, and those things all somehow relate to, in essence, what we're going to talk about today. I teach semester-long courses about all kinds of things in the data science neighborhood, and I also teach courses in things that have to do with software engineering and user experience design. In fact, the talk I'm going to give you right now would actually show up in two of my courses directly. I teach an SQL course and I teach a GIS course, both of those for obvious reasons that this talk would be there. The idea of how something like SQL gets hidden in ArcGIS and in other GISs also pops up in something like a user experience course, where we talk about decisions that designers make with their clientele in mind that can help some clients while hindering others simultaneously. All right, so what is a GIS? I'm probably in a room where I really don't need to belabor that too much, but I do know that there are some people registered for this talk that do not necessarily come from that background. So I'll briefly carry a little bit of that here. A GIS is an information system that has a geographic component, go figure. So somewhere, somehow, a GIS is going to concern itself with where something is, the geometry it has, the topology it has, perhaps georeferenced imagery, coordinate systems and changing them, elevations, terrain analysis, that sort of stuff. From data or information like that, you can answer lots of questions, derive lots of things, and augment all kinds of decision-making processes. Just like any other information system is intended to do, this one's just quite specific. More specifically, the goal of a GIS is to augment what we learn from a data set without geographic context, but in this case, giving it geographic context. A GIS allows us to visualize the data in a map, allows us to use spatial properties as part of selection paradigms, which is important for what we're talking about here today, and also allows us to conduct spatial analysis, be that spatial statistics or other mathematical techniques, perhaps relating to networks or that sort of thing. As an information system, a GIS effectively somehow is embedding a series of operations on top of some sort of data container that we call a database. There are 4 actions that a GIS has to be able to accomplish because it's an information system. It has to be able to create new data tables or files, read in data tables or files, update records within our data, and be able to delete data tables or files. On top of that, each of those transactions that GIS accomplishes has to satisfy several properties about those actions. Transactions, combinations of actions, are all or nothing in their accomplishment. This is called atomicity. So if any part fails, the rest of it fails. Data conforms to the rules of the database, namely consistency. Details of transactions are only seen by the user that makes the transaction. Otherwise, somebody else would see the prior form. That's isolation. And finally, once a transaction is completed, it persists. This is durability. So I only mention this because when we talk about the query engine, what we're talking about is the read operation specifically of those 4 actions. So that is important when we think about that. but it's also there are going to be parts of this talk that will relate to the consistency dimension, where we have data types that create different restrictions upon what is possible with those. So that has something to do on the consistency level as well. A modern GIS really operates on a paradigm of very particular type of database for the most part. That paradigm is called a relational database, a computing concept that's 55 years old now and still going strong. There's a couple of very particular ideas that are essential to this type of database, and they play a role in what you see in a GIS. Again, the only reason we're having this conversation is that SQL is a language for relational databases. First, every column has a specific data type, though it may change based on what column you're in. We see that all the time when we add new fields to a table where we're asked to declare the data type. For those with a programming background, this is different than a two-dimensional array. A two-dimensional array has to have all of its elements be of the same data type. Data junkies would call the format of rows, namely one of the dimensions of that array, in this case, a tuple. A more common vernacular that you might hear someone say today with languages like Python and R is that we have a data frame that consists of a bunch of tuples rather than an array of tuples. There's also a requirement on the row. It has to be unique. In a GIS, we typically get that accomplished for free by having an object ID placed on the data points. In database terms, we refer to this as a primary key or an index. While we don't ever really declare that in a GIS in this case, it's sort of inferred. When we create that object ID, it's helping us to access what geometric object is associated with that in the map. It's specifically identifying that item. Whatever the identification mechanism is for a row, null cannot be involved in that. We functionally don't have to worry about that with a GIS because of the underlying geometric object. The final thing, and this is important because of how we often will curate data and try to connect it, is that relational databases are typically what we would call normalized to try to prevent some pretty adverse actions that can arise from things that are either conceptually overloaded in a table or have a functional dependency. What we will often do as GIS professionals is to have several database files that we load in to associate with an underlying geometric file. You may be familiar with that in the form of a geodatabase. In that case, edits to the DBF don't influence the geometries, and the geometries don't influence the DBF. Shape or line metrics stay attached to the shape. Sensor measurements or table data or something like that remains an element of the various DBF files. We often will call that concept focus to get away from the term normalization. A good example is the way the American Community Survey from the U.S. Census Bureau condenses the data files that it has by breaking them up into categories about different sorts of demographic phenomena that researchers might grab several things from the same table and never have to consult the rest for whatever application they're dealing with, unless it is necessary to combine things from different groups. So why does that description matter? The way that data is structured determines how we're going to be able to query it. For those who have never worked with information systems beyond a GIS, I'll tell you that there are tasks that become really screwy if your data set is not structured in a quote-unquote good way, namely the way that you expect it to be structured. I think about data visualizations I've done that I've had to twist and prod a data set to get it the way I needed it to make the visual. I tell that to my students all the time and make them have to account for it because they're going to experience it in their professional journeys quite frequently, because if you need to make a dashboard, each visual has different needs. So instead of editing data several times, you learn to do the twisting and prodding. For a relational database, the query mechanism is SQL. When we talk about the read operation of the CRUD requirements we talked about earlier, that's what querying is. On a formal level, SQL implements what we call relational algebra in mathematics. On a practical level, SQL was constructed with a goal in mind. The goal was to have something that is relatively readable to a human. For its time, that was more or less a novel idea. Today, our programming languages are higher order and thus are a lot more readable. But when you see what SQL looks like, you'll have a pretty intuitive gist of what that's trying to accomplish on what and how, just by how it is structured. For the rest of the talk, we're going to be talking about SQL, and we're going to conduct what we often refer to as a crosswalk. How do I do this task that I typically do in platform X and do that same thing in platform Y? To do that, we're first going to talk about the math behind SQL and then put that in the context of what we do with data sets in ArcGIS, so you can see that the features of SQL are embedded in ArcGIS. The same is relatively true for other GIS platforms as well. So the foundational mathematics for tabular data are what mathematicians refer to as relational algebra. For those of you who have a math background, notice that I said relational algebra and not relation algebra. These are two very different things. Relational algebra works on relations, which are what we think of as tables in our vernacular. Relation algebra is about how sets relate to one another and the results of successive operations from that group. Joins are part of relational algebra. Something like De Morgan's laws, which we'll talk about a little later, are part of relation algebra. We're not going to talk about sequencing these operations implicitly. A database management system is structured to do that efficiently, and that's actually what algebraic systems are interested in as from a mathematical point of view. We're going to talk about the fundamental operations. We're going to break them into 4 general groups. Some operations are about looking at results from several queries or tables. Union, intersection, and set difference, which are 3 of the basic 4 set theory operations. The other is complementation, are from this idea. Unions combine sets into one. Intersections look for common things between sets, and set differences exclude things that are in common between sets. Some operations are about choosing what things are part of our output structure. Selection acts upon rows, namely what condition makes this row stay in my view or my interest. Projection acts upon columns, choosing to keep it or not, or combining data from within the row to engineer a different feature, such as a surface area from a table that would have length, width, and height of a package. You could also imagine someone reordering the columns in a presentation format. That would also be a projection. Some operations are about stitching or unstitching rows from several tables together over some mutual condition. These will be things that relate to a Cartesian product, join, and division, which would be what undoes those things. We'll talk about each of these, of course, in turn in a second. Finally, the last operation is about the logistics of administering a query, where something is leveraged multiple times or needs to be understood in another context, and that's the concept of renaming. You could rename a table, you could rename a column, something like that. It doesn't change anything except for how we refer to it. So let's look at each of the operations one by one. Selection is about targeting the rows in our data set that meet the condition that we care about. You've seen that term before in a GIS. You have an interface in ArcGIS that is loaded with things that called select by location, select by attribute, select by drawing, or whatever. These are all implementing this type of feature. They're identifying records that we need to leverage. Selection can have no result, but typically will have fewer results than the whole table because we're strategically choosing things somehow. Projection is the similar concept, but it's about the columns. Projection, however, can take several forms. We can talk about reducing the columns, namely hiding columns. We can talk about changing the display order of the columns horizontally. This is not to be confused with sorting. Sorting is about the order in which the records are presented. This is about the order in which the attributes are presented within the records. That's a little different. We can talk about calculating new fields from existing ones. That's a projection. Projection is one of the most important concepts in GIS, but not because of this necessarily. Map projections are literally the same thing. They transform one coordinate space into another. Tables are just a coordinate space between all of your attribute domains. So by twisting the way the space is oriented, that's just as much a projection as a map projection is. Renaming is pretty straightforward. Change how something is referred to. In the context of the read action in a database, renaming is not permanent. There is a keyword in SQL called alter that will make that type of change permanent. We'll return to that concept in our crosswalk a bit later. A Cartesian product, otherwise known as a relational product or a cross join, if you're familiar with terms like that, is a combination of tables row by row. Some people will refer to this as forking a table. For every row in one table, it will be combined with a copy of the other table. So you're going to have something that explodes in its size because it's trying to combine everything with everything else that's in the opposite set. For those who are familiar with graph theory, this would be called a bipartite graph as a representation. Join is an operation that's like a Cartesian product, but it involves a condition. This leads to confusion because note that in the purple box there, it says nothing about equal. It says everything about true or false. We expect that this is used with equality, and it most of the time is, but it does not need to be. There are several types of joins in the database world. An inner join only returns things that are able to be matched over the condition. Otherwise, it would get rid of the evidence of them altogether. Outer joins, there are three types of those, left, right, and full. They maintain information even if it cannot be matched. A left join will maintain the first table in its entirety. A right join will maintain the second table in its entirety. And a full outer join will maintain both tables, no matter if they can be matched or not. When I say maintained, I mean in the output data table that we're talking about, it's not going to delete the tables because you've done this operation. Natural joins have equivalent column names in their respective tables and also match equality on the records themselves. And equijoins have equivalent values. So they shorthand how you write the joins when you look at something like SQL, as opposed to inner joins and outer joins, which you have to specify a bunch of things about them to do that. Division is a mathematical necessity for the algebra, but it's largely impractical for SQL unless someone's a wingnut in putting together their data. The only reason that division should be implemented in a database management system is to undo an archival. There are ways to do it without an operation, provided that you know the original table structures in place. But this is not a function you will see in SQL at all. Unions combine records from relations vertically, so long as the tables have similar enough structure. So when I say similar enough structure, I'm referring to data types. So the columns that are one for one with these tables need to have the same data types, not necessarily the same names. If they don't have the same data types, they can't put them in the same columns for obvious reasons. Intersection searches for common rows between tables. So while unions are additive, intersections reduce. They specifically are looking for the ones that are in common. The opposite of that would be a set difference, which will exclude the ones in common. So in this case, we would remove anything that shows up in both tables. It is asymmetrical because the first table becomes the reference point. The second table removes things from the first table. So we have something that's necessarily asymmetric. A union of the asymmetrical set differences in both directions would be called the symmetric difference. I don't believe, I've never seen anyway, that concept showing up in an SQL, but you can create it, namely by using a union of the oppositely ordered set differences. You would be able to produce that. So for those last four things that we just talked about, sometimes a graphic is easier to understand what they're doing. A union's going to put both sets together. An intersection is going to focus only on the common part. The difference is going to focus on the parts of the first one that aren't in the second one. And the symmetric difference is going to union both approaches to that phenomena. So this type of image is usually quite helpful in that regard. So now we've talked about the math. Let's look at how SQL is written because this is going to start to bridge us into the GIS. In general, the relational algebra operations are implemented in what are called clauses of SQL. A standard SQL query might look something like this basic structure. Select is the verb here. SQL commands start with some sort of verb. It's an older programming language or scripting language, so that's to be expected. For those interested in SQL, select is one of the many verbs that you can grant users privileges to for a table or a view. That's a management concept for databases, database admin type stuff. Each clause has a different purpose. The only two that are necessary are the first two, select and from. To think about this process, what we're doing is we're grabbing a table, that's the from clause, potentially connecting other tables to it, that's the join and on clauses, filtering the rows of the tables based on some criteria, that's the where clause, aggregating those results if I need to do that, that's group by, placing some sort of conditions on any aggregations, that's having, choosing what to show the user, that's the selection, and sorting our outcomes, which is order by. There would be another term here, which would be limit, which would reduce the number of rows that I'm going to view. I want to see the first 10 of them or something like that. Notice that I described that not in the order it is in. There's a reason for that, and we're going to talk about that in a second. You'll also see as in here in the select clause up at the top. That's renaming, or aliasing might be another term you hear for that. At the bottom, I've listed union, intersect, and except. Except could be replaced with minus, depending on the dialect of SQL you were looking for. Because as I said before, those are the group of operations that sit between queries. So we have a standalone query, one of those words, and then another standalone query. That would be the structure of this language. What's interesting about SQL is that its coding order, the way we write it, is not the same as its execution order. In fact, I asked students speculative questions about this based on what they know about the language that is in the queries themselves. What must the execution order be, given the different things you know about how you can write a query? So you can kind of figure out the order of operations or the execution order by really talking through the scenario of what's at stake. And I think that's helpful to do that. I cannot work with any data unless I can get it from a table. That means from and join have to come first, because that's where we get our table data from. I can write conditions where and having that do not reference things that I show in the select clause. They have to come before that. And I can't have any condition on an aggregation unless I've aggregated it first. So group by has to precede having. Then I can determine what I'm going to show to you. And then I can window dress that a little bit by sorting it or limiting the output or something like that. The reason it's written this way is that you grant permissions to the verbs on a table to users. Therefore, the commands start with the verbs. For those who have used the .NET language before, something like Visual Basic, you may have seen what's called LINQ before, line integrated query. That language actually writes it in execution order. So when I teach .NET languages, I always point that out because they will see SQL in the future. So that gives them something to kind of reference about what's going on there. So what we're going to do now is take those concepts and spin them into ArcGIS. ArcGIS does not have an SQL editor in a proper sense, but it's really only, it does have one for a where clause only, from at least from what I have seen. That being said, all of these ideas are found throughout the GIS. So we want to get a sense of what the clause is responsible for in SQL, and then think about where we see those things in the GIS. So we'll start with select. Select, unfortunately, implements the projection operation despite its name. Project is not a really good verb because it's not readily understood, present company aside, because you all deal with making maps and coordinate transforms and the like. Select determines what we're going to have in our output structure, not what rows satisfy that. There's a difference. It's a bit like setting a data type for a variable as opposed to populating the variable, so to speak. There's 4 basic types of things that will happen in this clause. We're going to choose columns from our table to show and thus exclude the others. We're going to perform potentially some sort of aggregation function, such as a minimum. We're going to transform some values from one or more fields into a new value, such as a calculated field. And we can alias a column or a calculation to have the name we want it to have. In ArcGIS, these four different features of that operation are all accomplishable. Projection is done in the attribute table. So up on the top left there, you can right-click a field and hide it. Only do that after the fact, in my opinion. Recall that the order of execution, that the conditions can involve things that are not viewed necessarily. So you want to make sure that you have all of your faculties about you to restrict your rows. I haven't tested to see if a field is hidden, if I can still leverage it in a condition. I would think you could, but I don't want to stake my life on that. It's just as easy to do this after the fact than to do it before. Calculating a field is done as in the middle example there. After you construct a new field with the calculate button, you can name it, you can write your expression, whatever. You'll notice it has to grab field names on the left-hand side of that come from the table that it's in, and then it has helper functions to help transform that. Renaming is done using the tool called alter field. You specify the table, you choose the field, and you give it a new name. I said we'd come back to the keyword alter. This, unlike in SQL, when you rename something in a query, SQL is not permanent because you're just presenting something. The read operation doesn't do anything. But the alter command in SQL is a keyword that changes the table. The query portion of SQL implements the read operation, which just accesses the data itself. So alter field is a permanent change, so be aware of that. The other piece of the select clause is the aggregation. That's in the bottom left. Select shows us the results of the aggregation. It doesn't define the aggregation. That will come later. In the image, there's an E and an F on what's called statistics fields. These are the key points for this operation. You choose what is to be considered and what measure to take on it. Item G, the case field, we'll talk about that when we get to group by. From and join are our environmental variables, so to speak. They set the canvas for the rest of the query operation. You get your fields from the tables that you're identifying here. You typically see only two things going on in these clauses. We're either renaming a table using as, just like in the select clause that we saw before, or we're identifying a table to combine with another one and how we're going to go about doing that. So the three pieces of what that does are choosing tables, joining them together, and potentially having a spatial attribute join as well. So in ArcGIS, the most elementary concept there is choosing the table to work with. That's the thing on the left. Every single selection operation has that input row feature. So this is a common type of thing that you're going to do all the time. That's the very nature of the from clause on its own. If you want to join tables together, you right-click a layer and you select Add Join. You then get to specify several options, which is the middle window here. In a GIS, you have an added join type called a spatial join, which is on the right, which will allow you to join things based on a spatial relationship of some sort. Remember I said I designed the blood and guts of query systems in GIS. That last one there is my bag, so to speak. Notice in the join window that there's a checkbox for keeping all input records. This is the difference between what's called a left join, namely if you check that, or an inner join, namely if you uncheck that. If the match cannot be made, this instruction tells us what to do with it. Imagine you had a map of voting data and the returns weren't in yet from a precinct. We see that on election night all the time. Do you want the objects to still be on the map or not? Yes, you do, more than likely. You also want to know that they aren't attached, so that would carry over a null value so that it doesn't influence anything. Your symbology can then take care of that visual for you. If you uncheck this box, the polygons would go away. So the first case is a left join, the second case is an inner join. A couple of things to pay attention to when we talk about joining in ArcGIS and SQL. In ArcGIS, you cannot join or rename something mid-query. You join the tables together, and then you query the result of the join. In SQL, you do it all at once. The other thing to remember, one thing that often baffles my SQL students is that you can write a query that makes a join condition over something that isn't a carbon copy of itself. So I can give you a relevant example of this to the GIS world. 2 years ago, a graduate student of mine gave a talk at our annual conference about conceptual neighborhood graphs of raster relations. So think your select by location featured on a shapefile, but doing that on a raster image. We simulated data to help determine which spatial relations were neighbors of one another. Namely, we're deforming one object until the relation changes to something else. To determine which relation came next, we actually leveraged SQL to join the data over a condition on the rows in the same table such that certain properties were exhibited. The relations had to be different, so we automatically have a non-equal join here. Then we had something structurally that had to change as well, depending what the deformations allowed were. ArcGIS does not have the wherewithal to make a join over a condition like that. It makes its joins as what are called natural joins or equijoins, where the condition is fundamentally about equality rather than about the condition being true or false. I personally don't like that myself, and it's the type of thing I talk about in a UX course, where software designers often choose to bury things like SQL in the interface, preventing someone who knows what they're doing with that from being able to do it in favor of making it easier for a more novice or intermediate user. Filtering records, the where clause is typically where we really think about querying in a GIS world because that's the extent really of the querying mechanisms. You're all probably familiar with the feature select by attribute. That's what this is in a nutshell. The where clause helps us to determine which rows are satisfactory. What we're doing is constructing some sort of condition that can be evaluated to true or false about a record. If it evaluates to true, the record is displayed. If it evaluates to false, it's not displayed or it's not highlighted. Typically speaking, you'll find Boolean operators hanging out in this clause, just like in the on clause with the join condition or in the having clause, which we're going to talk about in a second. You also might see things like ordering operations, things like less than, greater than, stuff like that. Things about text, starts with, begins or ends, a regular expression, something like that, something that refers to a null value, whether a record's null or not, so on and so forth. Where clauses effectively are managed by the several ways that the GIS lets you select items. So we have selecting by layer, we are selecting by attribute, we have selecting by location, we have selecting features on a map itself, and we have the notion of switching a selection, which would be using not. So reversing the terms of our selection. So each of those is executing a different fundamental premise. Select by attribute is literally mechanically writing a where clause. You'll notice that there's an SQL button there right above where that's written. So you can type your where clause by using that if you're more familiar with it. Otherwise, it gives you a selection interface about the columns that you have, specifying the relation that they need to have to something else, and so on and so forth. And it can combine those with logicals such as and or. I'll point out select by location here specifically because this is one of the cases where we can talk about the reverse direction. What most SQL folks don't know is that there's a data type called geometry. We know that in the GIS community because we need it for shapefiles. Go figure. There's a function called strelates that derives a matrix encoding of the relationships between objects. That's how the concept of select by location works. My PhD supervisor is largely responsible for that theoretical research. I have further extended that myself. My PhD sibling, Jayant Sharma, namely, we had the same PhD supervisor, is high up in the Oracle Spatial team. There are similar functions for the specific relations you could have, such as separated, overlapping, touching, within, etc. I also find it really helpful to commit something like De Morgan's laws to memory. They're about how not works with and or. There's also the set theory equivalent of complementation over union and intersection. This is an example of multiple ways of proving the same statement. Sometimes one of those pathways is a lot easier to work with based on your data set or the tool you're working with. So it's helpful to be able to derive equivalent statements. Excuse me. Group by tells us how our select clause will treat aggregation functions, namely, what are they going to group together to perform the aggregation? So here's that image again about the summary statistics. We can access that by right-clicking a field and selecting Summarize. The case field can have several levels, which effectively is how we do a multi-factor drill down. For those of you familiar with, say, social psychology, think about intersectionality and how that would relate here. Does a single categorical factor tell the story of oppression or privilege, or does adding another level change the dynamics of that entirely for those different combinations? It's also something connectable for people who are statistically minded to a two-way ANOVA with an interaction effect. If there's an interaction effect, the combination of categorical groupings significantly alters the outcome statistically. The other key piece here is that the stats we can use in an aggregation are data type dependent. If something is stored as a text field, I cannot do an average on it, even if all the things in it are numbers. That often can throw people for a loop because sometimes we don't pay attention to what the data type is on a table that we're pulling in, and we're comfortable with the table itself. So we might get a surprise. That happened to me recently where I pulled in a table that had a space instead of nothing there, which instead of putting a null value there, it turned the whole column into text. So all of my numbers were text. And I was missing a null value that I should have had. So I had to do work to the data first to be able to do the summary that I wanted to do. Having works on the group by operator and its select outcome. We are placing a condition on the aggregation and using that to control whether or not it gets displayed. Having is only achieved by first exporting the table from the summary table, the summary tool we just saw before, and then selecting by attribute upon that outcome. So there's no direct way of implementing having from that perspective. Order by accomplishes sorting. It's one of the more straightforward things in SQL. In our interface in ArcGIS, sorting is accomplished by right-clicking a field and choosing the manner in which you want to sort it. You can do that ascending, descending, or a custom sort, which would be over multiple fields. This is very consistent with something like Excel or Google Sheets. It's a pretty common architecture overall. The three set theory operations are keywords that join the results of queries together. This can only happen if they have appropriately similar structure. Please don't confuse these with spatial union, spatial intersect, and spatial difference, which are tools in a GIS. Those are acting on the geometries only, not the tabular data. Of note, a set difference can be phrased as an intersection with the complement of the other set. This is a critical way of seeing that idea. In our selection tools in ArcGIS, you'll notice selection type is something that's there. This is the ticket for accomplishing unions, intersections, set differences, and complementation. New selection makes a fresh query, which dismisses the entirety of the rest of the selection that's already been made. So you would be starting anew. Add to selection is the union. It will append things that fit the new criteria, maintaining those that come before. Remove from selection is the set difference. It will take out the things that the new query identifies from within that group. Select subset from a current selection is the intersection. It will apply the new criteria only to things you selected before. Switch the current selection is complementation. It gives you everything but what you already have. As I alluded to before, one of the more frustrating things I've seen in the software development industry is to try to make things more intuitive for the masses, but while doing that, stripping away the power that knowledge of what's under the hood can provide. ArcGIS is such an example from my working with it. It chooses to disconnect the features of the select verb to prioritize a one step at a time UX. My first exposure to something like that was Oracle PeopleSoft that hid the join features and the aggregation features. I was staring right at several tables that I knew exactly what to do with, but the tools in front of me gave me no leverage with which to do that. It set us back and made much more labor for us. The point is that as a UX instructor, which I am, I understand what the appeal of doing that would be, but I question if it's totally a good decision to shut off the pathway to the known infrastructure entirely. It frustrates more seasoned users enough to make them search for alternative products, or at least that's what I've seen in the past in many different pieces of software. So the point of what we've gone through this afternoon is to recognize that nearly everything that ArcGIS can do on a query level, SQL can do, and vice versa. There's a couple of idiosyncrasies that we've pointed out. To my knowledge, ArcGIS doesn't make joins over non-equal conditions, which SQL can do as evidenced by a prior MEGUG annual conference talk. Excuse me. Similarly, ArcGIS can select records on the fly manually. SQL doesn't do that. What I want you to take from this isn't necessarily, let's go run and use SQL tomorrow. If people want to learn more about escaping the GIS software and working with tables in SQL, I'm happy to do a session on that specifically in terms of writing SQL, or have a community of practice where we talk about those things. But more importantly, what I hope that I've imparted here is that in reality, whenever we're talking about a query, we're working with a tabular structure. It's important, at least as I see it from a problem-solving perspective, to understand the guts behind these systems. They're running SQL on a database somehow. If we can take a readable language and break it down piecemeal, we can direct ourselves through the complexities of the interface to make that work. SQL is really the anchor here if you know what you're looking at. What's interesting for me is that I learned ArcGIS before I learned SQL. I teach both of them now. I still, to this day, when I'm sitting and trying to query something with a GIS, I still think in terms of the SQL. When I teach my students GIS, I teach them to think that way when they start using those select by whatever operations. When I teach SQL, I give this exact presentation because it highlights two things. One, it highlights beyond any shadow of a doubt what the execution order is. It becomes crystal clear by the steps that ArcGIS makes you take, and knowing that it leverages SQL behind the scenes, that the execution order is not the coding order. And two, that different software actually implements or window dresses or whatever term you want to use for that type of thing, that you're studying SQL, it has a way of doing that. If you learn to recognize the concepts in other things, you can transfer that knowledge. That's when you know you've made it as a data scientist. You can start to see the interaction patterns and then leverage knowledge of each of them in the other's context. That's valuable beyond measure. So with that, I want to thank everybody for their attention. I welcome any questions, and Becky will manage that. But here's that QR code again if you want to register to be part of MEGUG. So I'll leave that up here for like 20 seconds, and then I'll stop sharing. So
Thanks, Matt. We do have a couple questions and comments. Mike White asks, what spatial SQL languages are offered for popular relational databases? And if anyone wants to kind of elaborate on their question, I can turn, give you the ability to speak.
Yeah. So generally, what's going on with spatial SQL, to my knowledge, is what you're seeing is generally what we call the Clementini-Eggenhofer operators. So when you look at select by location, there are things like intersects, separate or disjoint, outside, touching, within, stuff like that. Those are things that are implemented directly from the Oracle language, which is where a lot of the SQL systems are coming from. But Python also has access to those types of commands through what's called the GeoPandas library. R has access to that through what's called the SF library, and their infrastructure is pretty much the same. You also have in select by location things that have to do with buffer distance and the like. That's really leveraging the geometric data type. So literally anything that's in the geometric data type that is a process that can be done on an object is accessible by the query language that is in the GIS. If I don't know if that answers your question, Mike, but that would be the way that I would treat that is if the geometric data type supports the operation and can resort to true false, that would then create an opportunity for a where clause to leverage it. So,
Okay. Andy Smith Peterson commented, ArcGIS can accommodate more complex queries, such as more complex select join conditions, etc., via a query table or a query layer.
yep.
It took me years to stumble on this. I use spatial views in the DBMS a lot as well.
Yeah. So for those who are using I don't want to say the vanilla version of the software, the tools to do the complex SQL things are very hidden. And that is something that is, I think, a disadvantage sometimes. You have to get a lot more specialized in it to get into the DBMS pieces. So that's what Andy's referring to.
Um, let's see. So in the chat, there's a couple of other comments. Robert Rogers asked, is there a spatial tolerance? Is there a spatial tolerance that separates within from completely within? I've wondered that myself.
Yeah, so the tolerance is so I can explain this by essentially the data architecture. So when you look at a polygon, which is typically where these two things are going to come from, when you look at a polygon, the polygon is stored in a series of tables. So this is about shapefile architecture for those who are aware of this or not. So your table is set up to have points identified and then edges that connect those points, and then polygons become a sequence of edges. So effectively, when you look at within and completely within, the answer lies within that data format. So completely within specifically has to share or it cannot share nodes. It cannot share edges at all. Period. Within, so long as the lines don't cross out, or they're outside or they're not outside entirely, that will trigger it. So that's the spatial tolerance level. It comes from how the shapefile is structured. Namely that you got to share a vertex to not be completely within, or you've got to share an edge to not be completely within. But if your footprint is inside the other polygon and you don't do those things, then that's where you get completely within. Does that
Someone
work for you, Robert?
I don't think they are able to speak,
Well, I
but
mean, it ended up in a chat, so
yeah. Someone asked, is it possible to get a recording of the session, this talk? And yes, I'm putting the link to our YouTube channel in the chat. And that will also be, once this talk is published in YouTube, I'll be sending out an update to all of the attendees with the link to it. Oops.
you sent that to just Mike.
Yep, I saw that. Okay. And I don't see any other questions in the Q&A. All right. Well, thank you, Matt. It's really informative. Actually, I had a question. Do you see, given that SQL and sort of the existing basic ArcGIS query system is so ingrained and we're all used to it, do you see anything replacing it at any point? Or
That's a good question. I think so. I'll take that from effectively things you see in the software industry generally. So in the software industry, a lot of types of things that you see is that people will develop things in house to meet their own sorts of needs. So there are all kinds of different software that companies make themselves that then they leverage internally and have proprietary control over and all of that. And the reason I mention that is because when we train students as a computer science professor, we don't necessarily want to teach them direct languages. We want to teach them how languages work, generally, like linguistically, because we want to prepare them for that environment. So the reason that I mention that in particular is that the antithesis of that is to then create systems that are not proprietary in nature that then can be user modified and freely built and leveraged across the board. So this gets you to things like Q, which Mike gave presentations on. He gives leverage to our next Lunch and Learn series speaker, Alex Burnham, about space time. R and Python have libraries that leverage geospatial data. The advantage that those things have is that they don't come with a cost. But the drawback becomes that you have to understand coding to leverage them more appropriately. Effectively, when you look at the software industry, when you have proprietary software from a company that has a lot of GUI work done to it, that's what you're paying for. You're paying for the user testing, you're paying for the environmental testing, you're paying for the technical support, all of that. So each of them serves its own purpose. One of them will get tools in the hands of people who need them quicker, but there's an overhead for it in terms of the amount of coding language you need. The other end of that is if you have the resources to get something with a more expensive license, you're paying to make the interaction with it perhaps simpler, but you are paying a cost for the quote unquote simplicity of the interaction. So do I think something replaces Esri directly or ArcGIS? I know Esri is one of our gold sponsors. I want to be careful about this. No, I don't think something directly replaces ArcGIS. ArcGIS is good at lots of things for various reasons. But that being said, it's not the only one. What you might see are changes in how data formats work, which then change lots of things. So Robert brought up the shapefile problem with completely within and within. If the shapefile architecture goes away, you have to think about, well, what does that look like now, right? So that's another sort of idea that you're talking about. So that's a complicated question, Becky, for several reasons. But I think you will see a diversity of these tools. So to answer that question, I think more directly, you're going to see a diversity of these tools, each of which having its own strengths and drawbacks. And you're depending on price points, you're going to need more knowledge of automating processes. You're going to have to understand programming a lot more for things that have less of a cost. Again, you're paying for user testing, you're paying for GUIs, that kind of stuff when you pay for proprietary software.
Okay, thanks. If there are no other questions, thank you, Matt, and thanks everyone for attending. And hopefully we will see you next month on the 11th.